So before I get into this first problem, it's worth introducing the tool that I used for these problems and that I'll use frequently throughout the course, and that's called the Desmos Graphing Calculator. And you can get this calculator on your smartphone, or you can get it on your computer just by visiting the URL, which is desmos.com. And when you get to the calculator, you just enter your equation that you're trying to graph, and it'll graph it there for you. So y equals 3 is just this horizontal line, as you recall, probably from algebra and pre-calculus. It's a horizontal line. And so when I take the limit as x approaches 5 of 3, here's my value 5. I'm approaching from the left side and the right side. And from both sides, we're just approaching an output or a y value of 3. So on these problems, you were asked to find the limit both numerically and graphically, and we just saw the limit graphically. And it's really not necessary. In the real world, it wouldn't be necessary to find this numerically because it was so easy to find it graphically. But I wanted to show you that this tool can also be used to find things numerically for the more complex problems. And it's actually very convenient because it sets up a table for you, and you can adjust the input values and come up with your output values. All right, and you do that by clicking on this wheel up here, and there's an icon that looks like a table. You click on that table, it will automatically fill the table with values, and you'll need to adjust those. And so what I've done here is since I was trying to find the limit as x approaches 5, I used that as my middle value. I chose values that were just below it, so 4.99, 4.999, and then values that were just above it to see what the limit was. And clearly, every value that you plug in has an output of 3, so the limit is 3. All right, on the second problem, we were trying to find the limit as x approaches 2 of 7x minus 4. So I've graphed y equals 7x minus 4, and I'm looking at the limit as x approaches 2. So here's 2, and we're approaching from the left side and the right side. And if you look from both sides, the graph is approaching the y value of 10. So in this problem, I also want you to note that if I ask you to find f of 2 and you plugged 2 into this function, you would get 14 minus 4, which is equal to 10, right? And so when the limit actually equals the value of the function at that point, we have a special name for that, and that name is continuous. All right, and we won't talk about that anymore this lesson, but we'll introduce that in a future lesson. All right, for this problem, I also wanted to show you your table. So I've created the table here, and you can see that as we're getting closer and closer to 2, that our y values are getting closer and closer to 10, aren't they? So that supports what we just found with the graph. So in this next problem, we're looking at the limit as x approaches 1 of x squared minus 1 over x minus 1. And so as we get close to the value of 1 from the left side and the right side, the limit is approaching 2. Looks pretty straightforward. What's interesting about this graph is that it's a bit misleading, okay? If you look at the values on the table, you can see that at x equals 1, the function is undefined. So if you were to zoom in on this graph, you would see a hole at x equals 1. Now, does that affect the limit? No, it does not affect the limit, but it does affect the continuity, which we talked about briefly in the last slide. So just wanted to make you aware that sometimes the graphs are a little bit misleading. I also wanted to make note of the fact that this was the self-generated table of values that I pulled up when I looked at this function, and notice that if you're not adequately close to 1, the values are not going to show you what the limit is. Now, if you put your own values in, though, and make them very close to 1, all right, you're going to see that the value of the function is approaching 2, which is the limit that we identified on the picture of the graph. I really just wanted to make you aware of a couple of things as you use your graphing calculator. Sometimes it can be a little bit misleading, and also the importance of picking values that are very, very close, very, very close to the value that you want to find the limit at. For this next problem, we're taking the limit as x approaches 0 of sine of 5x over x. All right, so as we're getting closer and closer to 0, here's 0, from the left side, it appears that we're approaching the value of 5, and from the right side as well. So if we look at the graph, we can see that the limit is 5. Just to confirm our answer, let's look at this numerically as well. So if you look at your graphing calculator, there's an icon at the top that looks like this. And if you click on that, it'll give you the option to pull up a table. And the table pulls up these values, x values, and their outputs as well. And it self-generates some values, and they're not very close to the value of 0. So if you're looking at limits, you actually need to change those values to become very close to the value of 0. All right? And if we do so, we see that as we get close to 0, our y values are getting close to 5. So this just confirms what we saw in the graph. All right, for this next problem, we're taking the limit as x approaches 3 of 1 over x minus 3. And I've combined a picture of the graph with the table, and you can see those values. And you can see that as this is the first problem that we've dealt with, where you're taking the limit from the negative side. So as you're coming from the left side or the negative side, the graph goes off to negative infinity, and you can see it here as well. So the closer we get to 3, at 2.999, we already have negative 1,000, and as we get closer and closer to 3, that number is going to get larger and larger. So it's going off to negative infinity, and then the limit as x approaches 3 from the positive side of 1 over x minus 3. As you're approaching 3 from the positive side, what's happening to the graph? Well, it's going off to positive infinity. And again, you can see that from the values here. As we have 3.001, it gives us output of 1,000. If we were to get even closer to 3, that number would get larger and larger and would go off to infinity. So there was an example like this in your lesson. It was f of x equals 1 over x, and we were taking the limit as x approaches 0. When we don't have the same values from the left and the right side, so if the limit from the left side is not equal to the limit from the right side, we say the limit does not exist. So in this case, we have a limit that does not exist. All right? This final problem is a bit different. Again, we're taking the limit as x approaches 3 of 1 over x minus 3 squared. And we want to find the limit as x approaches 3 from the negative side, and the limit as x approaches 3 from the positive side. And you can see that both from the negative side and the positive side, the graph is tending towards positive infinity, isn't it? All right, so this is going to be equal to positive infinity, and this is positive infinity. You can also see that on the table of values. Here's a number just on the left of 3, which gives us an output of 1 million, and here's one just to the right of 3, which also gives us an output of 1 million. So since the limit from the left side and the right side are equal, we can say that this limit is equal to positive infinity. You might also see it called an infinite limit or an unbounded limit, but it is definitely not, the answer is not, does not exist. Does not exist is reserved for if the limit from the left and the right are not equal to one another.